think this is the last example we're going to do for your assignment 3. There's some kind of good / bad / whatever news. The next section, systems of Laplace transforms, I have completely forgotten about in terms of assessment. And what I'm going to do is I'm going to give you a break, and we're not going to assess the next section. Now I am going to cover it, probably not until I'm up to date with my corrections. So what this all means is, well, it actually means that from after this lecture, you are going to be putting a lot of time into doing the Laplace transform exercises. And if you're not putting them in, look, I've told you, you have to put it in. If you're not doing it in, it's a bad choice. Okay, so here we go. Here's our last example and a testing one to go. Okay. So we'll write some stuff that we probably drew on previous ones for the last time. So here we have a differential equation in the time domain. That's the differential equation. We're interested in finding x of t, given this relationship between the function and its rates of change. And how we're going to do it is we're going to translate this, in particular translate the differential equation into an algebra equation. And it's going to be easy to solve the algebra equation, and then we're going to send back using the inverse Laplace transform. Okay, the formulas that are relevant at this time are that a second derivative gets sent to s squared times Laplace transform of the original function minus s times the value of the function in the time domain at 0 minus the value of the derivative and the time domain at 0, and the first derivative gets sent to, by the Laplace transform, s times big F of s minus little f of 0. Now in this question, the role of f is being played by x. Now this is not it's not a function of x. It's x is the name of the this thing, so it is in the time domain. Okay, so we do the Laplace transform of both sides. So the second derivative, we're using the first orange formula, but all the f's are x's. So I get s squared times not big F but big X minus s times not little f but little x minus little x dashed of 0 plus fixing the 2. Now we'll use the second orange formula. X dashed is sent to s times big X of s minus little x of 0, and the following bracket is very important. Plus fix the 10, and little x of t is sent to big X of s, and the constant 0 is sent to 0 over s. So that's the first step. Second step is to apply the initial conditions that x of 0 is 0 and x dashed of 0 is 1. So we get s squared times big X of s minus s times x of 0 is minus s times 0, which is just 0, minus x dashed of 0, which is minus 1, plus twice, and we can multiply this out, 2 by s by x of s, and 2 by minus x of 0, but x of 0 is 0, so it's 2 by 0. We'll just write it in just in case you're looking back and a bit confused, plus 10 times x of s equal to, well, 0 divided by s is just 0. Now we're trying to solve this for big X of s. We might just say that that's 0, that's gone, that's 0, that's gone, and all we have to do really is just add that 1 to both sides if we want to get all the x's on the left. So that's what we're going to do in the next page. So we're going to add 1 to both sides. Hopefully I can remember the rest of it. So yeah, so we have s squared times big X of s plus 2s times big X of s plus 10 big X of s equal to 1. So we take out the common factor of big X of S. And what are you left with? S squared plus 2S plus 10 equal to 1. And now to find X of S. So this is the algebraic equation that we're solving. This is easy to solve. Divide both sides by that quadratic. So you get 1 over S squared plus 2S plus 10. Now you look in the tables and basically what you want actually is that you can do partial fractions. That's what you want to be able to do. So you want to, i.e. you want to write X of S as a sum of simple terms. So what you want to do is, to do that, you do the partial fraction expansion. So the first thing is to factorize the bottom. Now, you do the AC method, so that's 1 by 10, you get 10, and look at the factors of 10, you get 1 by 10 and 2 by 5. 3 doesn't go, 4 doesn't go, 5 we already have. Now, can you make up plus 2 using a pair of these? No, you cannot. So that now, it might still be possible to factorize, but if you look at b squared minus 4ac, so that's the thing in the square root in the minus b formula, it's negative, which means no real roots and therefore no real factors. So there is no partial fraction expansion. Now that's very bad, okay? So that's bad. So what actually we're looking at instead now is that this didn't work. So we look in the tables again, and what we see is omega over S squared plus omega squared. And you think maybe it looks something like that. And in particular, what you're thinking is maybe it's like that, that's a sign, but shifted. So omega over S squared plus omega squared with the S shifted to S plus A. That's what we're thinking. And to write the bottom of this like that is to complete the square. That's what we have to do at this point. Okay, so we need to complete the square. So we want to write S squared plus 2S plus 10. We want to write this as S plus A squared plus omega squared. That's what we want to do. So I want to do this. So what we're going to do is we're going to, actually good question, can you substitute in values of S to do this? Yes, you can. You could substitute in, actually does that work very well? In theory you could. So you could substitute in values, say S equal to 0. And that will give you one equation, and S equal to 1 will give you another one. That is absolutely an option. Now I'll just show you that. They might say, oh, you're confusing us. And that's not what it's like. So S equal to 0, what do we get? On the left hand side we get 10 is equal to A squared plus omega squared, which we're going to get in a moment. And then say, so a clever value is actually S equal to minus A, but it won't run with that. So out about S equal to 1. So on the left hand side you get 13 is equal to 1 plus A all squared, so it'll be A squared. No, this isn't much cleverer, is it? And then what you can do is the A squared plus omega squared is actually equal to 10. See that? A squared plus omega squared is equal to 10. So you get 10 plus 2A plus 1. And we're going to end up with A is equal to 1. So that is another option, but possibly confusing. I think it's easier to compare coefficients. So multiply this out, you get S squared plus 2AS plus A squared plus omega squared. And now compare. So, well, first of all, the S squareds are equal, so no issues there. What about the coefficient of S? So it's 2 here and 2A here, so they have to be equal. And also the constant, so I have 10 here and A squared plus omega squared must equal 10. So we should start with 2A is equal to 2. And divide both sides by 2, I get A is equal to 1. So that's that done. And then I have A squared plus omega squared is equal to 10. And the A is equal to 1. So that's 1 squared plus omega squared is equal to 10. 1 squared, of course, is just 1. So take away 1 from both sides, you get omega squared is equal to 9. Now, algebraically, there are 2 solutions to this. So if you do square root of both sides, you have to be careful that there's actually 2 solutions, but we actually only need one of them. So plus or minus 3, but we'll use 3. Okay, so if you go back to the s squared plus 2s plus 10 must be equal to s plus a all squared plus omega squared, we find that a is 1 and omega is 3. So the x of s, which we found in the previous part, is actually equal to this. So it's talking about shifted cosines and shifted sines here. Now there's no s on top, so it's not really a shifted cosine. It's more like this thing down here. So this is so let's write something. So let's write that omega over s squared plus omega squared goes back to sine of omega t. Okay, and so if there's a shifting, if the s is shifted to s plus a, then this is what you call a shifted sine omega t. And this is kind of what we have here. Now the only issue is we have a 1 and we should have a 3 because you need to have omega. So we definitely want a 3. So we have to do a little bit of work. We'll see this on the next page. Or no, we'll see it here. So x of s, sorry. Okay, so x of s is equal to this 1. What I'm going to do is I'm going to multiply this by 3. Because if I multiply it by 3, I'll get a 3 on top. So maybe what I'll do is I'll write, if I multiply above and below by 3, this will do the job because the 3 over 3 is equal to 1, so that's not going to change anything. And I can multiply in the 3 on top and keep the 1/3 outside. So these things are the same. So do you see like that these are the same thing? Essentially what you can say is from here, you could, if you want, just say, look, multiply by 3 and divide by 3 and it'll be the same thing. So you could write an equals here. You don't need that line that I went through. Of course, this is a sine 3t, but it's shifted because instead of s, you've got s plus 1. So it's 1/3 times a shifted sine 3t. So we want to have a look at this. So this is 1/3 shifted. So look at the omega's 3, 1/3 shifted Laplace transform of sine 3t. Okay, so what does the first shift theorem say? If you're bringing back something shifted, you bring it back as normal, so you fix the 1/3. So the 1 over s squared, or sorry, the 3 over s squared plus 3 squared comes back as normal, sine 3t. But because it's shifted with an s plus 1 instead of an s, you multiply by e to the minus 1t. And that is the solution. And what you have here is, this is a wave, but this bit is exponentially decreasing to 0. So you end up with a wave, but the amplitude is decreasing to 0. Something like that. Okay. Is there any question about door closers here? Suppose that the differential equation models a door closer. Is it well designed? No, because the door is slamming. So, so not well designed. Now you can say that the door slams, so there's a slamming here, or else you can just simply say it's underdamped. Okay, so for a number of weeks now, ye are going to be working very hard doing exercises, and I said if you're not, I'm sorry, you're a fool.